Okay, hello everyone. My name is Amir Masoud Farahmand, and I'd like to welcome you to another talk from the Machine Learning Advances and Applications Seminar Series, which is organized by the Fields Institute and the Vector Institute. Today we have the pleasure of having Radford Neal, who has done a lot of great research in machine learning and statistics. So let me briefly introduce Radford. Radford is an emeritus professor in the Department of Statistical Sciences and the Department of Computer Science at the University of Toronto. He obtained his bachelor degree and master degrees from the University of Calgary and his PhD at the University of Toronto, where he worked with Jeff Hinton. His PhD thesis was on Bayesian neural networks and their implementation using Hamiltonian dynamics, which he has done a lot of work on it. He has worked on many aspects of machine learning, Bayesian modeling, Markov chain Monte Carlo, statistical computation, applied statistics, data compression, and error correcting codes. Today, he's going to talk about MCMC training of Bayesian neural networks. And yes, just please join me in welcoming Radford.
Thank you. So as you can tell from the intro, this is work that I've been doing for quite a few years, starting with my PhD thesis about 30 years ago. After a while, I went on to some other things, but I've recently been interested in getting back to this. There's also been work by other people recently, which I mostly won't have time to talk about along these lines, and trying to relate what you can learn from Bayesian neural networks to the current popularity of deep learning, for instance. So the talk, I'll start by describing what Bayesian neural network models are in the sort of theoretical sense of what they're supposed to be like, and then talk about how you can actually use them in practice using Markov chain Monte Carlo methods, at least for models and data sets up to a certain scale. The challenge is to get things to work for even larger scales. And I'll talk a bit about some experiments that I've done recently on seeing how far one can push Bayesian neural networks towards larger data sets, and a bit about what I plan to do in the future along those lines. So I assume you've probably all heard of multi-layer perceptron networks. This slide is sort of just to establish notation and such. We've got our networks are aimed at regression and classification problems, but the network itself just computes an output from some outputs from some inputs using some number of hidden layers in the usual sort of fashion that is diagrammed there. There are lots of variations on this, and I'll assume for what I'm doing that we might have some of these variations, such as direct connections that skip over some layers rather than going through each layer consecutively, for instance. And there are also schemes for how you don't directly connect everything to everything else, but have sparse connections with weight sharing and so forth, of which one big example is convolutional networks. So I won't go over the details on that. The crucial thing for Bayesian neural networks is that the network is just part of a probabilistic model. This is common for non-Bayesian methods as well, but there are also non-Bayesian methods that can't really be interpreted as using the network as a probabilistic part of a probabilistic model. But for Bayesian methods, you always have to see it as a probabilistic sort of setup in which the output of the network is used to define some distribution for a target variable. So for regression models, that's a real valued variable, and the output of the network might be the mean of a Gaussian distribution for that target variable, conditional on the inputs for that case. For binary classification, you can use a logistic model. And for multi-class classification, one uses typically what's called a softmax model in machine learning, or a multinomial logit model in statistics. And now for training these things, non-Bayesian training is very common, of course. And you can sort of distinguish between old style non-Bayesian training circa 1990, what the state was when I was doing my PhD thesis, for instance, which is characterized by perhaps viewing the training as being maximum likelihood estimation, in the sense that you do online gradient descent in minus the log probability of the targets, which is equivalent to doing a maximum likelihood estimate if you were to actually converge to the real minimum. But if you were to really do that, you would probably overfit quite badly. And so circa 1990, the approach to this would be, first of all, to limit the complexity of the network, not have too many layers, perhaps not too many hidden units within each layer. Sometimes this reached what seems, in retrospect, at least, as being somewhat ridiculous things of people doing hypothesis tests as to whether they need 3 hidden units or whether only 2 hidden units would be good enough. But the typical feeling was that you had to somehow limit the complexity in order to avoid overfitting. Although there was the alternate approach of using regularization, such as weight decay, along with your batch or online gradient descent as a sort of another way of avoiding overfitting. And one could also stop training early, at times deliberately with a validation set where you could see when you should stop. But also a lot of the early work in neural networks seems in retrospect to have used early stopping accidentally. Their computers were simply too slow to actually train for long enough to overfit, and so they got good results. So a more modern practice with deep networks and such is that to use much more complex networks, not using the idea that you have to limit complexity in order to to avoid overfitting, and much more data. But even though there's much more data for many problems, the networks tend to be much more complex. So it's not clear that the data is so large that overfitting wouldn't be a problem. And it's typical to do gradient descent with mini batches, I think primarily for computational reasons, although that also has effects on what the learning is like. And there are stochastic modifications to the learning, such as dropout, that are intended to alleviate overfitting problems. And people still do early stopping and create ensembles of a bunch of training runs with the predictions being averaged together. So you could ask, well, yeah, but why does this all work? And now, if you've encountered any fanatical Bayesians before, you'll know that the Bayesian answer to this is that, well, if it seems to work, it must be because it's some approximate Bayesian method. So, and there's some justification for that. Things like ensembles are very reminiscent of Bayesian methods, and things like dropout have also been looked at as being approximate Bayesian methods. And so that's one reason to look at Bayesian learning more explicitly, is to see whether it does give some insight as to whether the methods that are used nowadays, as to why those methods seem to work well. So the Bayesian approach to neural network models, or to anything, is based on treating everything in terms of probabilities, and in terms of probabilities that capture all the information you have, both your information from the data and the information you have beforehand as to what the relationship you're trying to learn might be like, what's called prior information. Now, this doesn't make much sense if we have some small network, like because we don't really believe that whatever function we're trying to learn actually has the form of the sum of 3 tan-h functions, for example. So that's just completely unreasonable from a Bayesian point of view if you're trying to build a model that captures your prior information. But it's quite reasonable if instead you think you have many hidden units, because with many hidden units, you can approximate any sort of function arbitrarily closely, as has been proved for many, many decades. So then is a reasonable non-parametric model, a model that doesn't impose any tight constraints on what the relationship might be. And so it seems like a reasonable thing to use based on prior information. The challenge would just be to set up the details in accordance with what you believe the nature of the problem is a priori. Now, if we do use a network with many hidden units, then if we do maximum likelihood estimation and we actually really find the maximum, we're probably going to drastically overfit. But of course, that's not what the Bayesian approach to learning is. The Bayesian approach doesn't try to find a maximum, the best fitting network, which turns out to be very overfitted, but instead looks at probability distributions through the whole process. We start with a prior probability distribution over network parameters that's supposed to represent what we think the actual function might be before we see any data. Now that might seem challenging for a network that's hard to understand, but it is actually possible to make progress on understanding what you're doing when you set up prior distributions for network parameters. And then once we have the prior distribution, we incorporate the information from the data to produce a posterior distribution for the parameters. And then finally, when we want to make predictions for test cases, we don't predict based on any single value for the parameters in the network, but instead average the predictions of models of the model with over the distribution of parameters that we found when we formed the posterior distribution. So our prediction is an average over theoretically like the continuous distribution over parameters, in practice perhaps over a sample of parameter values from that distribution. This is very similar to the ensembles that many people use in order to improve predictive performance, except it's sort of central to the whole Bayesian idea rather than a sort of add-on that you decide to do an ensemble at the end as well. Now, ideally, we set up our model and our prior based on our understanding of what the problem is like. But in practice, of course, we're somewhat limited in our understanding. We can't totally understand these complex networks, and we're also limited in our computational resources. So those are the basic challenges of trying to do Bayesian inference is our limited intellectual capacity to understand what we're doing with our models and our limited computational resources. So as far as the intellectual understanding goes, one way of trying to make progress on that into understanding what the prior distribution on network parameters might mean is to just randomly sample from the functions computed by networks that have parameters set according to our prior distribution. So here's an example of that. We'll have a network with one input, one output, two hidden layers with 100 tanh units in each layer. And we give distributions, Gaussian distributions to all these parameters, the weights between layers and the biases for the units, except I gave the weights on the from the last hidden layer to the output a Cauchy distribution rather than a Gaussian, just to liven things up here. And if we do that, we get functions that look like this. These are I guess it's actually 5 functions, not 4, drawn from this distribution. And you can see that they have a variety of characteristics. Some of them are sort of almost constant with a few wiggles. Others have substantial variation with a few little bumps here and there. If you've done this exercise before with all Gaussian priors, you may notice that this isn't quite what you get with Gaussian priors. The Cauchy distribution here actually has an effect, and we'll see why that is later on. So that's one way of getting insight, is you just actually sample some functions and see what they look like. And if they don't look like what you think is a reasonable function for the problem you're trying to solve, then you know that you should try a different prior distribution. But it's also very useful to look at the theory of things. And in particular, we can look at the theory as the number of hidden units in a hidden layer goes to infinity. So in particular, suppose we have just one hidden layer, and we'll give all the parameters independent Gaussian prior distributions, and then look at the limit as the number of hidden units in our hidden layer goes to infinity. For one component of the output function, we can see that it's equal to the output bias plus this weighted sum of hidden unit values, with the V's being the weights. And if we look at what happens here as we let n go to infinity, well, if we gave bk a Gaussian distribution, it'll be Gaussian. And this sum will become Gaussian by the central limit theorem, provided that each term has finite variance. And well, if the hidden units have, say, tanh activation function, that's a simple case, then the function is bounded, and the fact that the V's have Gaussian distributions guarantees that this is going to have finite variance. So as we let n go to infinity, this term also becomes Gaussian. And furthermore, if we just scale down the distribution for the VKs to have a standard deviation that scales as 1 over the square root of n, then this will converge to a Gaussian distribution with a finite variance. And then the sum of those will be Gaussian. So the output at this particular input, x1, will have a Gaussian distribution, a Gaussian prior distribution in the limit as n goes to infinity. And the same is true for the outputs at any other x value. And in fact, the multivariate distribution of the outputs at a whole bunch of x values will also converge to a multivariate Gaussian. This is what's called a Gaussian process, in which we have a collection of points, an infinite collection of points, in this case, possible values for x, where any finite set of them have a multivariate Gaussian distribution. And Gaussian processes are very well studied objects in probability theory. So we now have a much better understanding of what's really going on with the Bayesian neural network, with what the real implications of the prior distribution on parameters is. So here's an example of such a function from the Gaussian process defined by a neural network. Well, technically not necessarily a Gaussian process because it only has 10,000 units rather than an infinite number of units, but this is enough so that it's very close to being Gaussian. And you can see there's two inputs on the horizontal axes and the function value on the vertical axis, and it has sort of a blanket over rough surface sort of appearance to it that comes from a general smoothie sort of prior. We can figure out more details of this sort of prior as to whether it actually is smooth, for instance. We can figure out what the correlation functions are like and figure out that we'll end up with smooth functions in certain cases if we, for instance, have smooth hidden unit activation functions, but we'll have more locally Brownian functions if we use, say, a step function for the activation function. In either case, it's important to realize that as in the limit of an infinite number of hidden units, the importance of any individual hidden unit goes to 0 because we're scaling down the magnitude of the weights as 1 over square root of n. And so as n goes to infinity, the weight from any particular hidden unit to the output goes to 0, and each individual hidden unit only has a negligible contribution to the result. That's interesting in that it means that there aren't really any hidden features being discovered by this network, which was one of the sort of goals of neural networks originally, was the idea that these hidden units would compute sort of significant features of the inputs. But in this sort of limit, all the hidden units have negligible impact individually. You can extend this whole argument to having more layers. As long as you keep making everything have finite variance. And that makes, in some sense, it makes the neural network seem less interesting because in the end, even if you add multiple layers here, you get just Gaussian processes, which are very flexible objects that you can do a lot with Gaussian processes, but maybe not quite as much as you were hoping to do with a neural network if you had ambitions of things like discovering hidden features. Another thing that makes this result another reason why this result makes neural networks seem less interesting is that once you've realized this, you can actually do all the learning without actually having a network, because once you can compute the covariance function of the Gaussian process, you can actually do all the learning and inference using matrix operations without any actual network being used. Although, of course, if the matrices get big enough, maybe this starts to be a bit tedious. Maybe you do want a network after all. But it seems that this result tells you something about the limits of this sort of particular prior for a neural network. Now, fortunately, there are other priors you can use for a neural network. In particular, ones based on what are called symmetric stable distributions. The concept here is that if you have a bunch of variables from a symmetric stable distribution of index alpha, which can be between 0 and 2, and you add them up, they're independent, you add them up and scale by n to the -1 over alpha, you get a random variable that has the same stable distribution of index alpha. And furthermore, so you can see this is well known if the x's are Gaussians and you scale by n to the -1/2. And in fact, the Gaussian distribution is the symmetric stable distribution of index 2. And just as for Gaussian distributions, you have a theorem, the central limit theorem, about how sums of independent random variables with finite variance converge to Gaussians if you scale them like this. There's a generalization of that, saying that in the case of independent random variables that don't have finite variance, the sums, when scaled appropriately, will converge to one of these symmetric stable distributions of an appropriate index. So the upshot of that is that the argument about the central limit theorem that we did before for Gaussians can be applied with prior distributions that don't have finite variance in such a way that we converge to one of these non-Gaussian stable distributions as the number of hidden units goes to infinity. We just have to scale in the right sort of way. So for instance, for tanh units, which have a bounded value, so that eliminates some complications. If we use a Cauchy distribution as the prior for the weights out of the hidden units to the output, and we scale as n to the -1, then we end up with a suitable limit as n goes to infinity, because the Cauchy distribution is actually the symmetric stable distribution of index 1. And more generally, we can use t distributions and get the other symmetric stable distributions. Now, these priors for neural networks have quite different properties from the Gaussian process priors. For one thing, the hidden output weights that have this, when we give them this prior with infinite variance, they don't all go to 0 as n goes to infinity. Asymptotically, a few of the weights still have substantial size. They actually, another way of looking at this prior is that the weights come from a Poisson process, which has a singularity near 0 with an infinite integral. And so most of the weights are very close to 0, but a few of them are bigger than 0. And that means that individual hidden units can have a significant effect, that there can actually be hidden features found from the data as represented by these hidden unit values. These priors are, I think, much more interesting than the Gaussian process priors. But unfortunately, analyzing them is also much more difficult. Gaussian processes are very tractable mathematically in a way, but these non-Gaussian stable processes are much less tractable. There's also no sort of trick for just directly doing the inference without actually having a network. So that means if you set things up to produce non-Gaussian effects, the actual neural network might be useful after all, because there's no direct way of just going to the model with an infinite number of hidden units without actually using a network. So here's a example of using these sorts of things. This is for a network with 2 hidden layers, the parameters and 2 inputs and 1 output. And the parameters all have Gaussian distributions except for the weights from the second hidden layer to the output, which are given a t distribution with 0.6 degrees of freedom. And this doesn't have finite variance, and it will converge. So this will converge to a non-Gaussian stable process. And these are just 2 random samples. And you can see that the appearance of these functions of 2 inputs is quite different from the appearance of the Gaussian process. Which way are we going? There, you can see the sort of wavy blanket here from a Gaussian process versus these things, which look much more like mountains and such. There's sort of, you can see sort of like a region here that's depressed in a way that doesn't at all look like the wavy blanket from a Gaussian process. So that's one interesting aspect of Bayesian neural networks is you can produce significantly different, interesting prior distributions by controlling how you're giving prior distributions to the parameters like that. Another important aspect of Bayesian neural networks, which I think is underappreciated in some of the recent work, is that it's very important not just whether you have a Gaussian prior, for instance, but also the details of what the standard deviation of that prior is. So if we give a prior to weights in a neural network with one input, one output, and one hidden layer, the standard deviation of those weights, if we give them a Gaussian prior, has an effect on what the function looks like in terms of how smooth it is, that is, what scale of wiggles there are. So here are two sets of three functions, each drawn from a Gaussian from a neural network with Gaussian priors, but we change the standard deviation of the input to hidden weights here. And when the standard deviation is comparatively small, we get functions that vary over fairly long scales of in terms of the input. Whereas when we increase the standard deviation, we get ones with much finer grained wiggles. Now, if we're trying to model some data, we probably don't know ahead of time how wiggly the functions are going to be. So we don't want to fix this standard deviation at 5, say, and then have it turn out that actually the functions aren't that wiggly after all. Instead, we want to make this standard deviation be another parameter, which in Bayesian terms is called a hyperparameter because it's a parameter that controls the distribution of lower level parameters. I should note that in recent years, machine learning people have appropriated the term hyperparameter to mean almost anything from your learning rate to how many GPUs you decided to use. But in Bayesian statistics, hyperparameter has a very specific technical meaning as a parameter in a probabilistic model that controls the distribution of lower level parameters. So that the real prior distribution for those lower level parameters could be obtained by integrating away the higher level hyperparameter, which you might sometimes decide to do. But the reason we often put in those hyperparameters is because the model is easier to understand in this sort of 2-level form, or perhaps multiple levels, in which we have low-level parameters that are what actually matters as far as the distribution of the data goes. But then rather than directly give a prior distribution to those, we give a prior distribution that depends on higher level hyperparameters, and then give a prior distribution to those hyperparameters and perhaps go up a few levels that way. And that produces models that can express complex dependencies between the low-level parameters in an understandable sort of way. And so that's the specific meaning of hyperparameter in Bayesian statistics. So in addition to fairly simple things like how wiggly do you expect your functions to be, you can use hyperparameters in Bayesian models to express more complex things, such as which features are actually relevant, which input features are actually relevant to predicting the target. And in the context of a neural network, we can, for instance, have a hyperparameter associated with each of the input features, which controls the variance of the weights out of that input separately for each input. And then if we learn that hyperparameter for the standard deviation of those weights should be very small, that effectively makes all those weights be almost 0, and that input has very little effect. Whereas if we learn that hyperparameter should be large, then that input will have a large effect. And remember, we aren't fixing this a priori. We assume we don't know originally which inputs are actually relevant. If we did, of course, we could just do things manually, but we'll assume that it's a complex problem where we don't understand the relationship yet. And so we want to set it up so that the model itself can learn which are the relevant inputs. And that will be the case if we make the weights out of a particular input have a distribution that's, say, Gaussian with a standard deviation particular to that input. We give that standard deviation a prior distribution. Typical one would be a gamma distribution for 1 over the variance. And then that might depend on a yet higher level hyperparameter, which we in turn give some distribution. And then this sets up a complete probabilistic model for both the hyperparameters and the parameters, which then fits the data in such a way that captures whatever can be learned about the real nature of the relationship as to which inputs are relevant and such. So supposing we've set up our model like this and we've somehow come up with a posterior distribution, we might wonder, how do we actually make predictions? And well, in the Bayesian framework, we make predictions by averaging over the posterior distribution. So our prediction for the target in a test case, given the inputs for that test case, is conditional on all the training data and is found by integrating the predictions for that test case with particular parameter values theta times the posterior probability of that theta given all the training data, which is in turn proportional to a product of the prior distribution and the likelihood, the fit of the training data with those particular parameters. Now, this is not going to be anything like an analytically tractable integral. So we have to do some sort of approximation or use some sort of Monte Carlo method. In a Monte Carlo method, we replace this integral by an average over values of theta that are randomly drawn from the posterior distribution. And that's going to be the method that I'll be looking at. Okay, so I should perhaps quickly say again what the benefits of all this are supposed to be. One is that we're supposed to be able to understand what we're doing here if we're doing things in a Bayesian way. We're trying to express our prior beliefs about the problem. It's not supposed to be just some sort of black box that for no particular reason we decide to do boosted decision trees or something or other. We're supposed to actually, in theory, have a reason why we chose this prior distribution. And because the whole thing is set up in a probabilistic fashion, we should end up with probabilistic predictions that incorporate all of the uncertainty, not just the inherent uncertainty in the problem, but also uncertainty from our limited knowledge from limited training data, for instance. And as I've talked about, we can hope to learn high-level aspects of the problem, such as which inputs are relevant, and we should expect that we avoid overfitting unless we set up the model in the prior in some very strange way. Of course, to get these benefits in practice, you have to be able to actually do the computations. And so that's what I'll go to next. So there's various ways people have tried to do Bayesian inference. I'll skip right to the Markov chain Monte Carlo method, since I'm running out of time here. And for Markov chain Monte Carlo, in particular Hamiltonian Monte Carlo, which was invented by the physicists doing quantum field theory, but which I learned about and used for Bayesian neural networks, works very well for problems that are of small to moderate scale. So I did a bunch of work showing that a while ago. So it'd be of interest to know how far can one try to push these methods towards bigger problems, particularly with faster machines and so forth now. I'm not going to be able to explain Markov chain Monte Carlo in any detail here, but the basic idea is you do a Monte Carlo, an MCMC run by starting off with some initial values for parameters and hyperparameters. Perhaps you just choose them at random from some distribution. You simulate a Markov chain that is designed so that it eventually converges to the posterior distribution for these parameters and hyperparameters. And then you use the iterations from that chain after some point where you think convergence has been reached to estimate the predictive distribution for a test case by averaging the predictions of networks using parameters from each of those iterations that you got from your Markov chain. There are many ways of setting up Markov chains that converge to the distribution you want. The sort of most famous is the Metropolis algorithm, in which you propose to make some small change to the state, and then you accept or reject it based on how that change affects the posterior probability. You always accept if it makes it higher. You sometimes accept if it makes it lower, depending on what the ratio is. So that's a very general technique that's very widely used in physics and statistics. Now, unfortunately, in its simple forms, the Metropolis algorithm is just hopelessly slow if you try to use it for Bayesian neural networks for any sort of substantial size problem. Fortunately, Hamiltonian Monte Carlo works much better. Hamiltonian Monte Carlo uses the gradient that you get from the usual backprop procedure in order to move the parameters in a way that changes them by a substantial amount, while avoiding the penalty of doing a random walk in little steps. If you do random walks in little steps, then to get n steps away from where you started, you typically have to do n squared changes because many of your steps double back on themselves. And so that gives you that sort of n squared penalty from doing a random walk rather than systematically going in one direction. So each HMC update consists of randomly sampling what are called momentum variables, that one momentum variable for every parameter. And those momentum variables get you going in some direction in the parameter space. And that's why you avoid random walks, as you keep going in the direction established by the momentum variables, well, subject to how you have to move in order to get the right distribution. These momentum variables are actually part of the Markov chain state, and so they count in figuring out the probabilities of states. We then simulate approximately, because it's too difficult to do exactly, a trajectory according to Hamiltonian dynamics based on these momentum variables and the parameters we have. Hamiltonian dynamics is basically the dynamics of real life, and you can see this as simulating the trajectory you'd get from a puck sliding around a uneven surface that has ups and downs. It'll sort of speed up as it goes downhill and then slow down as it goes uphill and slide around in this way. And Hamiltonian dynamics is the dynamics of how that works. And in this context, the height of the surface the puck is sliding over corresponds to minus the log posterior probability of the parameters. And so we have the location of the puck corresponds to parameters, and the speed of the puck corresponds to the momentum. And we have to simulate this trajectory with in little steps, typically done with what's called the leapfrog method that uses the gradient that we have. And then we accept or reject the endpoint by the usual Metropolis criterion. And now if we actually simulate the trajectory exactly, we'd always accept, but we have to instead simulate it inexactly. And this accept reject step perfectly compensates for the errors in that simulation. So we get exactly the correct result, even though our simulations of the trajectories are inexact. So in figuring out why HMC works well, the crucial thing is that by simulating this Hamiltonian dynamics, we can propose a point in the parameter space that's distant from the current point. We set off in some direction according to what momentum we sampled, and we can travel a long distance in that direction unless we come to a hill where we'll sort of slide back down again. And furthermore, there's a very good chance that we'll accept that point, at least if we set things up properly. If the dynamics were simulated exactly, we'd always accept, but we have to actually do it inexactly in small steps that introduces error. But one of the crucial things is that in many cases, it's not like guaranteed to always be true, but in many cases, the error stays bounded. It just oscillates up and down along the trajectory. So here, for instance, is the error in log probability of parameters and momentum along a HMC trajectory from a starting point that I picked from a run for a CFAR 10 model with 239,000 parameters. So this is a reasonably high dimensional parameter space where you might think somehow the errors are going to sort of blow up or something. But here's the error from 0 is the log probability at the start state, and then we simulate the trajectory in little steps, and we can see that the error sort of stays bounded here. In this particular case, the error is usually negative, which means we'd accept. That's too much to hope for all the time. On average, the errors tend to be positive rather than negative. But either way, as long as they stay bounded like this, you have a reasonably good chance of accepting the final point, as opposed to if the errors just got bigger and bigger, right? And this is a sort of remarkable feature of Hamiltonian dynamics, or the inexact simulation of Hamiltonian dynamics, that relates to how, even though we're simulating the trajectory inexactly, the simulation perfectly preserves some properties that relate to the that relate to symplectic geometry, which I'm not going to go in. And that's somewhat of an explanation as to why this error remains bounded. Of course, if you start doing too big steps, the whole thing becomes unstable. You have to do sufficiently small steps to get this behavior. But once you're in that region, you can do very long trajectories without the acceptance rate going way down. So it's crucial that you do manage to set the step sizes to reasonably good values. And so this is one aspect of my work on getting HMC to work for neural networks. The basis of the heuristic procedure for setting step sizes is to try to come up with estimates of the second derivatives of the log posterior probability. But in order for the MCMC method to be valid, you can't actually evaluate the second derivatives, because that would undermine the reversibility of the procedure that's crucial to proving that it gives the right answer. Because the actual second derivatives at the start point will not be the same as at the end point. And so if you use those, the thing wouldn't be reversible. If you started at the end point, you wouldn't get back to the start point. So instead, you have to use information that doesn't change along the trajectory. And in particular, one can use the hyperparameter values, provided that the HMC is only changing the parameters and not the hyperparameters. So that's one motivation for why in the methods that I use, the hyperparameters are not updated as part of HMC, but instead are updated in separate Gibbs sampling steps. There are other reasons for doing that as well. But one is that you can then use those hyperparameters to set good step sizes for the HMC. So despite all those good things about HMC, it can still be pretty slow when you're trying it for extremely large models and such. And so there are various ways of trying to speed it up, some of which go back quite a while, and others of which are more recent, but all of which I think I don't have time for. So I'll go on instead to some experiments. So the software I use for these experiments is a package that I've written called Flexible Bayesian Modeling Software, which does neural networks and also some other models like Gaussian processes and Dirichlet process mixture models and so forth. The latest release of a few weeks ago is aimed at making neural network models more useful for larger scale problems. And this is done first by some architectural features that you can now set up convolutional layers and so forth, and also performance improvements that it is optimized for SIMD instructions on CPUs and allows computations on GPUs with CUDA, and has various nifty MCMC methods. You can get this from my webpage or from GitLab. And the goal of producing this new version is, there are two goals. One is to extend the scale of problems for which Bayesian neural network models are actually the preferred practical solution. There are, of course, real problems out there of all scales, from little data sets of 25 observations up to ones with 25 billion observations. So any extension of what you can do what scale you can use Bayesian neural networks for extends to another set of practical problems, right? But the other goal is to learn about the characteristics of Bayesian methods and larger problems, even if maybe the computation is a bit much to be used in practice in many cases. So I have time for just for a little bit about some actual playing around. I haven't done all that much playing around yet, because as I said, the new release is only a few weeks old. But here are some preliminary playing arounds. One task is what's called the Bioresponse task, which is a Kaggle data set. You're supposed to predict whether some molecule produces some biological response based on some features of the molecule. Now, the details aren't documented, perhaps because it's a Kaggle data set and they don't want people to look around for other data of the same sort in order to win the competition. But it's a bit unfortunate from the point of view of setting up a prior distribution and such that fits the problem. There are 1,776 input features and one binary target as to whether that molecule produces the biological response or not. If you just look at the data, you can tell that the features actually come in 6 groups with different properties that are with consecutive indexes, although nothing is mentioned about that. But it seems quite plausible that these 6 groups have different relevance to the task. And so I've tried to account for that in setting up a model. I used 300 cases for training and 751 for a validation set. And then I have actually tried a bunch of models, but here's one that has 17,457 parameters, which is not much by deep learning standards, but is enough so that there are some challenges from the HMC standpoint. This model is supposed to be set up so that various hyperparameters can try to learn what the real situation is regarding this data. So there are 6 initial hidden layers which don't connect between each other. They just all connect to the input. And the 6 hidden layers connect to inputs only in one particular group. Remember, there seem to be 6 groups of features. And so one hidden layer in this initial group connects to one of those groups. Within each group, there are hyperparameters for each input, so that even within a group, it can learn that this input in the group is more important than this other input in the group. But furthermore, there are hyperparameters that control the relevance of the entire group. So you might learn that, well, the second group is not really very relevant to the task. Then after those 6 initial hidden layers, they all go into a layer of 48 tan-H units. And then there's a second layer of 16 tan-H units connecting to the previous one. And then both of those layers connect to the output with hyperparameters controlling how big the contribution to the output is of the first of those tan-H layers and the second of those tan-H layers. That way, the model can learn whether those extra hidden layers are actually useful or not. It's also possible that the extra hidden layers can help initially in getting to convergence, but even if they aren't very prominent in the final equilibrium distribution. So that's the model setup. And here are training and validation errors during the MCMC run. This is squared error, just squared error between the binary response and the predicted probability. Red is on the training cases, and green is on the validation cases as you go along the iterations in the run. So we see that the training error mostly goes down, although it doesn't go down monotonically because the MCMC procedure is stochastic. It's not supposed to eventually reach an optimum. Instead, it's supposed to eventually reach a equilibrium distribution in which it just fluctuates around some average value. And we see it going down in the first 200 iterations, and this is the longer run here, going out to 4,000. And we see the training error does seem to sort of more or less have stabilized here. The validation error goes down initially and then starts going up again, which you might think indicates overfitting. But it does eventually also reach sort of an equilibrium distribution here. And the fact that it actually goes up in this point is not actually necessarily bad from the point of view of Bayesian inference here. Because these are validation errors using a single iteration to make predictions. But we don't use a single iteration to make predictions in Bayesian inference. Instead, we average predictions over the whole posterior distribution. So the fact that individual iterations are getting worse does not actually say that much about whether the average is getting worse. So that's just a look at the training run. And now we can look at predictive performance when we do average over iterations. And I'll look both at squared error and classification error here. Oops, there. The red plot is the squared error and classification error when using individual single iterations, which is, as I said, is not what you're supposed to do with Bayesian inference. Instead, you're supposed to average over the posterior distribution. And we can start by averaging in groups of 5, consecutive groups of 5 iterations. So that's what we get with the green line here. And you see that the error goes down considerably when we average over the iterations. The green line is much lower than the red line. And then we go on to 25 iterations for the blue line, and 250 iterations for the magenta line, and finally 1,000 iterations for the cyan line at the bottom. And we can see that averaging over more iterations gets us, generally speaking, lower error. And furthermore, eventually the idea is we should reach some equilibrium in which if we average it over more and more iterations, eventually we should get a horizontal line here, which hasn't quite been reached yet, but is sort of getting there. You'll notice that things do get slightly worse at the end than the beginning, which I suspect is just random. Like we haven't, like as we increase if we extended the run and averaged over more iterations, it wouldn't necessarily be the case that that we still see a rise at the end, although it's possible there could be a slight rise. There's no absolute guarantee that the equilibrium distribution is better than some non-equilibrium point earlier on. But if we have a good model, we expect that the equilibrium distribution will give good predictions. So this shows the hyperparameter values, some of the hyperparameter values controlling how much attention is paid to the different groups, which I don't think I have time to go over in detail, but you can see that actually starting about iteration 2000, it seems to have settled down as to which groups are more relevant. So I've also tried things on CFAR 10. So I've tried out a model with 239,000 parameters, 3 convolutional layers and 4 fully connected layers after that, whose details I won't go over. And you can once again see that training error goes down with iterations. Validation error goes down and then goes up again. But if we start averaging over iterations, we once again see that here, this is squared error, this is classification error. So that's why they aren't the same. But if we use individual iterations, we get a fairly high classification error. If we start averaging, we get fewer and fewer. One thing here is I switched from an inexact but fast method to the exact but not so fast method at iteration 300. And that may be the reason why the average of 258 iterations at the end is not as good as earlier, because there's less diversity of the iterations with the slower method. I'd have to go for more iterations to get equivalent things. Okay, so I have very little time left here, so I'll just mention that there has been other work by Ismailov and et al. On doing Bayesian neural network learning with HMC for large networks. They use very large computational resources, 512 TPUs, and they found that you could indeed get very good performance on many problems, but they also found a couple of things that seemed to me to be funny about the hyperparameter values that they actually fixed rather than changing during the run, having very little effect, and a strange result about the Bayesian predictions being poor when there's distribution shift. And so those 2 things I'd like to try investigating myself. And other things I'd like to investigate are how best to update the hyperparameters. You may have noticed in some of those graphs, there are very long-term correlations for hyperparameters over the run, which indicates that there would be considerable scope for trying to get things to sample better. So that might be a good thing to try to figure out, as well as figuring out which combination of all the various variations on HMC actually works the best. And it would also be good to get more insight into non-Bayesian deep learning from looking at Bayesian learning, and also to try out some applications at a moderate scale that's possible now with current GPUs and such, which might not have been possible before. And so those are some of the things I'd like to investigate. And I'll now switch forward to the bibliography so you can actually see the references I've been doing. And so that's it.
Well, great. Thank you very much. It was a very interesting talk. I think we have several minutes for questions. And just before that, I want to mention that we have a roundtable. So if you want to, people want to ask questions or stay around, we have time for that until 4:30. So yeah, if anyone has a question, please go ahead. So maybe I ask a question first. My question is that, okay, so do we know anything about some form of lower bound and what is the best MCMC approach? Like Hamiltonian MC, of course, improve over, say, metropolis-based approach, but is it supposed to be maybe the optimal way of sampling from the posterior?
I'm not sure that's a well-formed question in that HMC, for instance, uses the gradient information that isn't used by other MCMC methods. So you could, you might have proved those other, nobody has, but you could imagine somebody proved that, oh, those are the optimal ones, but assuming that you don't have access to the gradient. But then as soon as you do have the access to the gradient, you can say, ah, well, this would be better with HMC, right? So similarly, well, I'm not sure that anybody has come anywhere close to proving HMC optimal, but even if you had, on the assumption that all you had was the gradient, of course, well, there's no particular reason there couldn't be something else you could use, right? So it's hard to imagine how you could prove that HMC or any other MCMC method is in any useful sense the optimal one, and that you shouldn't spend any more time looking for a better one. You might prove things in much more narrow contexts, that some particular acceptance criterion for HMC is the optimal one, but that wouldn't prove there wasn't some entirely different method that worked better.
Yeah, I guess I'm kind of thinking like in the context of optimization, for example, we say that with this level of information, like zero order, first order, then we have something with this class of functions, say strongly convex, we have this, say, Nestrov accelerated method. And I'm wondering whether there would be any parallel type of results for the sampling.
Well, there are various results of how fast these methods converge in making assumptions, for instance, like the distribution being convex or something like that. There are also results about how things scale with dimensionality. Okay. In particular, another reason why HMC is attractive for Bayesian neural networks with large numbers of parameters compared to some sort of more traditional statistical problems is the scaling with dimensionality for HMC tends, under various assumptions that maybe don't apply in practice, but if you make those assumptions, the scaling for HMC is better than the scaling for simple-minded metropolis methods. So the difficulty tends to go up as n to the power 1/4 versus proportional to n, or the various other methods have other scaling factors, but HMC's scaling is comparatively favorable. But on the other hand, it still does sort of get worse at the rate of n to the 1/4, which, if you make n sufficiently big, you can see that that's going to be a factor in slowing down HMC.
Okay. Thank you. Are there other questions? Yes, there is. Yes, there's a question. So please go ahead.
Hello, Dr. Neal. Thank you very much for the great presentation. So I'm a researcher in civil engineering, actually, and I am very interested. I'm interested in various Bayesian inference methods, and these days I learned that there are methods called variational Bayesian method, and so I heard that some some machine learning guys have been using variational Bayesian methods instead of sampling techniques to train neural networks. And so I just wonder, I just want to hear your opinions about variational methods.
Well, one thing you can sort of deduce is that I'm working on MCMC methods, so I must not must think that those are more promising than variational inference. Variational inference works on you have some comparatively tractable class of distributions, and then you try to select which one you're going to, in that class, you're going to use as an approximation based on this variational criterion. And the problem is that the posterior distribution for a Bayesian neural network is extremely complex. And so it doesn't seem likely that you can get anything like a good approximation to it from whatever your simple class of distributions is. I was only able to just briefly mention this work by Ismailov et al., right, in which they one of the things they did is they tried using, complete brute force to sample from posterior distributions with HMC, and then compare them to, one thing they did is compare them to what you get with various approximate Bayesian methods, one of which was a form of variational inference. And they found that the variational inference, even if it gave sort of reasonably good answers in a practical sense, wasn't mimicking the results found with HMC very well. So, even if in some practical sense they might both be giving equally good results, say, the actual form is different, like they're making different errors on the test cases or something, right? So it doesn't seem as if the variational inference actually is a very good approximation to what the true Bayesian result is. Now, of course, that doesn't mean that it's of no use, particularly if it's faster. But it does mean that if you're trying to understand how Bayesian methods, what is going on with Bayesian learning in these complex models, that maybe saying, oh, well, we'll just do variational inference isn't getting you the true nature of Bayesian inference on that task.
Thank you so much.
So we have another question.
Okay, so I think Graham is having a question. Please go ahead.
Yes, thank you. Thanks, Radford, for the really nice talk. I was wondering.
You're still mute for some reason.
Oh,
really? I can hear him.
Oh, okay. Radford can hear me. That's good. Radford, while we're on the slide, I was just wondering, in terms of the HMC that's implemented in this paper, I saw this presented at a NeurIPS workshop, but I haven't read this paper. I'm just curious, how does this compare to sort of the 1990s version of HMC? Has it evolved a lot, or is this what they're implementing here at this larger scale, basically the same method?
Well, maybe I'm biased here, but to me, the HMC they use seems primitive compared to what I was doing in 1995. In particular, they don't attempt to do any sort of heuristic for setting the step sizes for different parameters, which means that they're just sort of arbitrarily using the same step size for two parameters, for which there's no particular reason why two parameters should have the same step size. You want to give some thought as to the relative step sizes that are appropriate for those. So as I, where are we here? As I, yep, here we are. So for different parameters, you need different step sizes. So if you have a weight that's from an input to a hidden unit, and the input has a typically large value compared to a weight from a different input that typically in the training set has a small value, well, the effect of changing the one weight is much bigger than changing the other, and you need to adjust your step size to account for that if you want to not avoid wasting time by having a much smaller step size than you could have got away with if you'd picked proper relative step sizes. And they don't do anything like that. They just sort of set up their model in whatever arbitrary fashion it was set up, and then just use the same step size for everything, adjusting it so that it doesn't diverge, so that the dynamics doesn't diverge, which must be substantially inefficient, I would say. They also have a interesting but probably not desirable approach to how long the trajectories are, which is that they try to make the trajectory long enough that it will have sort of moved to a completely different location as far as the prior goes, which is somewhat arguable, might be okay, but I'm not sure. So it's possible that it's very inefficient in that respect too. And the biggest thing is that they don't do any adjustment of hyperparameters. They just fix all the priors for parameters and don't have any hyperparameters, which is sort of throwing away one of the large advantages of Bayesian learning from my standpoint. So it's interesting that despite all that, they do get quite good performance with enormous cost on some of these problems. But I think one can do much better than sort of doing very simple-minded HMC. They probably also don't do things like windows at the ends of trajectories and such, which improve your acceptance rate and other such things.
Thank you.
John, please go ahead.
Hi. Thanks for the
Hello.
talk. I was just wondering, this is probably mostly a comment, not just a question. Did you experience during the experiments any difference while using a tempered posterior instead of the posterior retrieved directly from HMC?
When using which?
A tempered posterior, the cold posterior.
I didn't, you mean doing a different, not doing the, okay, so this is something people have investigated, that rather, in Bayesian inference, the posterior distribution is defined as proportional to the product of the prior times the likelihood given that based on your trading cases. And there's only one posterior here, that is the right one, but you can decide that you'll change that you'll say raise the posterior density to some power and renormalize or sample from things according to that, and then get a modified posterior that might be either more or less concentrated than the right one. And some people have claimed that that there's a cold posterior effect, in which that if you make the posterior more concentrated, or you use points from a distribution that's a more concentrated form of the posterior, that you get better results. I haven't tested that myself. This paper here claims that that's an artifact of how they set up their data. I can't say, I haven't confirmed that myself, but another claim of this paper is that cold posterior effect is an artifact of setting up funny data sets in which the cases aren't actually independent, for instance, whereas the model assumes they are independent. Of course, if the model knew they weren't independent and actually accounted for the dependence, then presumably things work out okay. But if you put in data that's dependent and then use a model that doesn't know it's dependent, then, well, perhaps fiddling the posterior might be of benefit since it's not really the right thing. But assuming that if all the assumptions of the model are correct, you wouldn't expect that changing the posterior from the one that's the right one would be helpful, right? And that seems to be what they've found, but I haven't confirmed that myself.
Cool. Thank you.
So maybe we can call it like the end of question periods, but so we don't need to record it anymore, but people can stay around. We have about 15 more minutes for this